So welcome everyone coming to this first talk of this afternoon session. Our speaker is Professor Pei-Ying Lin of National Taiwan Normal University, Earth Science Department. Let me say a few words first now to introduce Professor Lin. And she was graduated from National Central University in her graduate study, and then she went to Arizona State University, Temple, to do her PhD. So after her PhD degree, she went on to LAMO, the Earth Observatory of Columbia University, for 3 years. And then she returned to Taiwan as a researcher for the Taiwan Ocean Research Institute in Kaohsiung. And then after 3 years there, she went to NTNU, National Taiwan Normal University. Now she's an associate professor, and her specialty, as you will hear, is on plantary, interior plantary seismology. And in fact, she's one of the few lunar scientists in Taiwan, so she's very precious. So Professor Lin, please go ahead.
Thanks for Professor Ye's introduction. And hi, everyone. First, I really would like to thank the invitation from Professor Ye and Taiwan Space Union, TSU. And as what Professor Ye just said, my research has been focusing on seismological and geophysical observation to study Earth and planetary interiors, so Earth and Moon. I'm particularly interested in multi-scale structures in the planetary, and it can tell us the dynamics in the Earth and Moon. Unlike most of the seismologists, including me, the same, we all prefer to deal with high quality data. But actually, I have been fascinated, falling in love with the relatively noisy data, but with abundant signals recording in the ocean bottom or other planets like Moon and Mars. So while Professor Ye discussed with me about the talk topics a few months ago, I was super happy to hear that some of you are interested in the planetary interiors and also moonquakes. So actually, today, I'm not going to talk about the moon. From the comparative planetarologies, actually, I'm going to share with you what we know about the interior of Earth and Moon by comparing and finding their similarities and the differences. So the reason I was happy to know some of you cares about planetary interiors is that most of us all care about, not all, most of us most of the time care about the surface or the things above the surface, because we can see it, we can touch it, we can observe it. But we really quite don't know what happens beneath the surface of the Earth or the Moon. Although we feel earthquakes, like people in Taiwan feel earthquakes, we know something happened beneath the surface. But really, because we cannot see it, we cannot really sample it from the surface to the deep core. So so far, we really don't totally understand what they happened and how they happened. The reason, as you may know, the difficulties to investigate the inaccessible planetary interiors, mainly due to high pressure and high temperature condition in the planetary interiors. So I don't know whether you know that or not. The deepest hole we drill, the human being drill on the Earth, the deepest one is about 12 kilometers, only 12 kilometers. But as you know, the Earth's radius is about 6,000 kilometers. And the reason we cannot drill as deep as we want, mainly because the high pressure and high temperature. So we even cannot assess Earth's mantle or core. It's really impossible for us to go and sample the things like direct samples or drill a hole for other planets with a larger pressure and a higher pressure and temperature. So, but as we know, as those who are interested, we really want to know the planetary interiors because we want to know its structure, what it look like beneath the surface, what's the composition of it. The composition might tell us the composition might tell us the temperature, the pressure of this, and then if this can tell us the evolution of the planetary. So as I say, since we cannot drill a hole, and so what else we can do? I using seismology, because seismology is one probe to investigate invisible astronomical body interiors. When the earthquake happens here, and the waves travel through the body of the earth and are recorded at the seismic station. Here is the time, and here is the distance from the earthquake to closest to the father. And each black line shows the record recording in this station due to this event. So these seismic waves actually carry the information of the present structure along their path to the surface. For example, so if the earthquake happened, the P wave, direct P wave and S wave sample to the mantle, and we can know the mantle structure. And for this phase, we call it PKP phase. The PKP waves, when the earthquake happened, travel to the mantle and go into the outer core and go into the mantle again and recorded the surface. And they bring out all the information it goes through and recorded the station. So seismology actually using this kind of signal to look for and understand the structure in the earth interiors. So all the planetary interiors, the first thing we trying to look for is layering structure. As we know that the planetary is constituted of the crust, mantle, and core. And here, this is the one of the Earth 1D model. We call it PRAM. This present the velocity and the density as a function of depth in the Earth. And so, for looking for a layering structure, actually, reflecting energy is super powerful. So, reflecting energy actually will show up when we have very strong seismic impedance contrast. By definition of seismic impedance contrast is the product of the density and velocity. So if you see this model, you can see at the core and mantle boundary, we have a strong seismic impedance contrast. Then we will have a very strong refraction energy due to this interface. On the right, I'm going to show you a movies of the wave field propagate from the earthquake in the deep. A deep earthquake happened in the earth about 500 kilometers depth, and I'm going to show you the wave field and also the red path of SCS, denoted in green. So you can see when the earthquake happened, the wave field that propagate all the way. And there's a waves actually will reflect at the core mantle boundary and back to the surface, and we record it. And in seismology, we call it SCS. The small c means reflection, and the reflected from the core mantle boundary. And actually, it can be seen in the data pretty well. So this is a real data. And this is an event happened in the 2011, January 1st. This is one of my lovely events. So you can see here, this is S and this is SCS. So you can see this SCS phase clearly in the seismic record. So that indicated that, so this is just, although we know it, we know Earth, there's a core, but this also lets you see we do have a direct and clear seismic phase reflected at the core mantle boundary. Okay, and that was one of the ways we try to understand the layering structure in the Earth. But as you know, the Earth is not simple. Beneath it is not like really like simple layering structure. Actually, we have plate tectonics and we have tectonic. Earth is tectonic activities. So actually, the surface, the structure beneath the surface are different beneath different area. So seismology, we use another way. We use the waveform and to see, or travel time to see what the velocity structure along the red path. So here, I was going to show you a movie, and actually, and there you will see the seismic wave of an earthquake at a depth 2,000 kilometers depth, and then this is modeling, and then we model. There's a station. The team model. There's a station here, and the red lines will shows the blend lines. Go to the blend line first. The blend lines shows the seismograms only for the layering structure. So everywhere is the same. Everywhere only have a velocity as a function of the depth. So that's the blend line. And the red line seismogram is showing that this is if there is a slow anomaly in the mantle. And this is the red line shows what we will observe at the station here. And here I was going to play the movies. Okay, can you see? So when the earthquake happened, the wave propagate in all the direction. And once it hit the slow anomaly, actually the waveform deformed. Not only waveform deformed, but also you can see the arrival times comes later because we travel to a slow velocity anomaly. It takes longer to travel to the station. And also when the wave propagate and hit this slow anomaly, and the waveform actually, the wave field actually distort, and that you can also see in the waveform variation, the difference between the red one and black one. So seismology actually use this kind of difference, and not only travel time difference, but also the waveform difference to looking for the structure beneath the Earth's surface. I just tell you that how powerful the seismic wave is, but actually, if you need a nice seismic wave, means that you need to have a seismic event, and you need to have a seismic event, and also you need to have a station to record it. So on the Earth, we are lucky because as what I just mentioned, Earth is tectonic active, and it so far is a unique planet, has plate tectonics. So as you can see here, earthquakes mainly occur at plate boundaries, and you also can see clear seismicity corresponding with the downgoing subducting slab. And take example, here is a Tonga Trench, and a very active tectonic region in the Earth. And you can see the earthquakes happen from the surface to the deep. On the other hand, for recorders on the Earth for over 50 years, many of the broadband seismic sensors are deployed in the Earth's surface, and even some in the ocean area. So lucky us as seismology, if there's an earthquake happen today, in my office, we can hit a button and we can get thousands of seismic data from these all stations just by hitting one button. So because we have this abundant earthquakes and abundant stations on the Earth, and we are able to see what's going on, try our best to see what's going on beneath the surface. And as we all know, that Earth won't be only layering structure. Actually, this is a result from the seismological methodology I just mentioned before. This is what we found. The red means the slow things, and the blue one means the fast velocity structure. As you can see, there are lots of structures beneath the surface. including a lateral variation. Lateral variation usually larger scale or small scale heterogeneity. There are lots of small scale stuff beneath the surface. If you see this image clearly, you can see the slab subducting in the west, in the Northern America, and actually in the Central Pacific, you can see the red things, the slow stuff in the bottom of the mantle, and these actually are the two main features of the plate tectonics, and that's how we know the seismology helps us to know not only fast and slow, but also tell us the evolution of the Earth. Okay, and it's not only tell us, but also because that those things we see here, actually, those structures we see here, actually, they are chemical and physical effects based on the PD condition. So PT, pressure and temperature condition. So this is observation, and this is our interpreted structure. You can see we are not only have layering structure, not only have across the mantle core, but also we have a slab subducted to the mantle, and we have stuff going up, and then we have like drying anomalies in the bottom of the mantle. So this actually we know them based on the seismological observation, and this can tell us the chemical and physical properties for this different structure, and then tell us the pressure and temperature condition in the Earth. The pressure and condition actually very important in the Earth because it also can explain the melting process. In the planetary, all the planetary evolution are very important, interminated related to melting process. So melting process actually happen a lot in several planetary interiors. So actually, in the simple way to say it, there are three ways to melt the mantle. So there are three ways to melt a rock. So here is temperature, here is some pressure, and this is a rock, it's a solid rock, and there's a line called solidus, and when you cross it, and the rock stop partial melt, and when you cross the liquidus, it becomes liquid. So this is it. Everybody know it, and this is what happened in lots of planetary interiors. So if we are going to melt this solid rock, there are three ways. The first way, I bet, it's all coming in your mind immediately. The first way is raising the temperature. If you're raising the temperature, the rock, this solid rock cross the solidus, and you melt the rock. And alternative, the other way is you lower, the other way is you lower the pressure. By lowering the pressure, you also cross the solidus. So, and then it start melt. We call it partial melt. So this is the two ways that you can easily to think about. But the third way is actually a tricky way, but it happened all the time in the Earth. Is that we move this solidus. So by adding the chemical composition, or you adding some volatiles, such as water or carbon dioxide, actually you can move this solidus to here, and then your rock start partial melt. So in brief, this is the three way to melt a rock we know we explain in the Earth and other planetary interiors. And this is showing you very common melting called decompressional melting or lower pressure. Actually, melting the mantle or melting the rock, the rock in the planetary interiors by lowering its pressure, or by decompressional melting, is the most common mechanism in the Earth interior. So what that means? So if I have something hot from the moving up from the deep Earth or deep planet. And when we're moving up, actually, is a lower. Moving up is a lower its pressure. Once it lower to some depth, it will start to partial melt. And so this is like we actually on the surface we see all the time. So like the basalt at the mid-ocean ridge, actually is most of the basalt in the mid-ocean ridge was generated by this mechanism. So although I say that the seismology is powerful to study planetary interiors, but actually there are lots of different ways. For example, magma actually is one of the ways. We can sample the magmas or all the basalts on the surface, and then we can see what's the composition beneath it, what's the composition inside it, and we can know what's the chemical or temperature beneath it. So this is one of the ways we know about Earth mantle. So most of the information about mantle heterogeneity actually, right? Most of the mantle heterogeneity actually infer from the basalt. So it's all come from the partial melt. So actually partial melt is a very important process in the Earth. Not only the basalt we observe, not only the shallow structure in the shallow depth, but also at the lowest mantle. Here is showing that the seismic observation for lowermost mantle, which is close to the hottest core. And so this is core mantle boundary, and this is core, this is the lowest mantle. And from seismology observation, we see lots of anomaly happen in this area. And the velocity in this depth close to the core is actually, there are lots of area actually super slow. Super slow, usually when we have super slow, usually like we interpreted it as a very hot area or there's a partial melt. So here I show you a geodynamics and thermodynamic models. As you can see here, so because it is a core mantle boundary, this core is the core is hotter, and if there's an area, actually the temperature is higher. The temperature is higher, it might cross the solidus. Once it crosses the solid, it starts partial melt. So it happens it can happen, and it happens in different area in the Earth lowest mantle. So melting process actually is a very important mechanism or phenomena in the planetary interiors. So again, here is observation-based structure, seismological observation-based structure, and here is the inferred structure and also showing some dynamics. I want you to notice here, there are two, I already mentioned, there are two highest anomaly. Here and here, there are two giant anomalies beneath the Earth's surface and at the lowermost mantle, very close to the core. Although we cannot go to there, but seismology observation already tells us that there's a huge mystery stuff there. And actually, and it happened beneath two areas. Where are they? Actually, one of them are beneath the Africa. One of them are beneath the Central Pacific. So there are two giant low velocity beneath the Earth's surface, and particularly in beneath Pacific and Africa. Fed said in 2019, 2 years ago, and he said our words. They are among the largest things inside the Earth, but yet we literally don't know what they are, where they came from, how long they have been around, or what they do. So there's a giant stuff in the core mantle boundary, and we observe it from seismological observation, but we really don't know what it is and how long they have been there. So lots of researchers and scientists actually looking for the hypotheses or ideas, what they are and how they form. This year, actually, a crazy hypothesis came out. And this was done by Yan and Mimi, my friends in Arizona State University. And they presented it this year in a PSC conference talk. So they came out with a very crazy hypothesis. This giant high density and low velocity beneath on top of the core mantle boundary, they might be the fragments why still iron rich things, and when they bump into the earth, actually some of them actually remain in the earth, and based on earth dynamics, this thin fragment actually they sink down into the earth mantle and bury here for a long time. But we got lots of so there are lots of interpretation of this low velocity or the giant anomaly. But I pretty enjoy this. I love crazy hypothesis because it can explain some chemical composition similarities between Moon and Earth. Actually, not only this crazy hypothesis. Actually, next hours, the talk given by Dr. Locke from Caltech, and he will share with you another interesting idea called synestia. So synestia actually is another ideas about formation of Earth and Moon, and try to explain why we see lots of chemical similarities between Earth and Moon. So I'm deeply looking forward to his talk. Man, I hope that you can. I know that you will stay here for another hour for his talk as well. Okay, finally, I talk about the Moon. Okay, so as what I mentioned before, seismology is a powerful tool to explore the planetary interiors. But the most important thing is that we need to able to observe and record the motion of the surface. Therefore, we need seismic sensors. And Moon and Mars are the other astronomical body with a certain amount of seismic data available other than Earth. Apollo mission, about in 50 years ago, in the 1960s, 70s, and astronauts deploy the seismic stations on the lunar surface. Here is image of the for the Apollo 11 missions. The astronaut Dr. Andrew with the seismic experiment, and you can see that this is solar panel, and this is seismometers, and then there's an antenna just pointing to the Earth so that we can get the data. So in 50 years ago, the astronauts help us to deploy the seismic stations on the lunar surface. 50 years later, the human being are smarter. So for the InSight mission, it is an ongoing mission. I bet most of you already know it. But the InSight mission, actually, we use robotic arm on the lander and to deploy the seismometer on the Mars surface. So this is true, and today this is true that we have available and useful data to study the planetary interiors other than Earth. And today I'm going to only focus on the Moon. And this is a sample of Apollo 11 seismograms. Yoshio Nakamura, he's at the University of Texas in Austin. He said that when they received this record, he said that we have no idea what these events were, because this is the first time we have a seismometer on the Moon, on the other planets, and the signals doesn't look like earthquake signals. So in the beginning, they really don't know what they are. And then Nakamura's group in 2018, they identified several types of seismic events on the moon. Therefore, we honor him as the father of lunar seismology. And after they carefully analyzes more than 10,000 events recording during the operation of the Apollo mission, so roughly about 7 years. So several types of the signals were detected from this Apollo mission seismometers, including the impacts. There are artificial impacts, so like when lander lands on the moon surface, or natural impact, like a meteorite impact. And as you can see, they are rare. There are only about like 9 artificial impacts, but more than 700 meteorite impacts during this period. So rare and frequent. Not only the signals from the impact, but also they identify 2 types of moonquakes. One based on the depth of the moonquakes. So one type is a shallow moonquakes. These shallow moonquakes usually occur about like 50 to 20 kilometer depth of the moon. And actually, there are not many. There are only 28 shallow events be recorded. And another one is deeper. We call it deep moonquakes. These 2 deep moonquakes is natural events occur between the 700 to 1200 kilometers depth in the Earth. And actually, they are abundant. There are more than 10,000, 1,000 deep moonquakes happening in the moon. And how do we know it? Actually, it's based on the waveforms. Here, showing the 2 examples for the data recorded at station 12, and then for the artificial event for different components, for 3 components, and this is artificial event, it's a meteorite impact. And you can see because they usually happen in the shallow depth, and so they have more similarity waveforms. And this is the impact. And these are the waveforms for the shallow moonquakes and deep moonquakes. And as you can see that the shallow moonquakes is similar to the meteorite impact, and the deep moonquakes looks a bit different. And easy to think about it because the depth of these 2 might be close, and this depth of these 3 might be close, and the source of these 2 are close. So that's the reason they have the similar waveform. And the deep moonquakes is the other one that we are surprising, and lots of works actually done by the data recording from deep moonquakes. Okay, and we go back to reality. So this is showing the seismic events on the Earth and the moon. Some is a station on the Earth and the moon. And this is a seismic event on the Earth and the moon. So as you can see, we are lucky to have a few stations on the moon, but actually it's not as many as what we have on the Earth. And also, the moon is not quite seismic active. So there are not many seismic events compared to what we have on the Earth. Even though we are still trying to use this data set to know more about the moon, because this is very precious. And then first, let's compare the difference of the seismic events between Earth and Moon. So this is a cartoon plot made by the Pei-Ying Lin in my team, in my group. And Here is the moon, the Earth radiance from 0 to about like 6,000, and this is moon, and from the moon from 0 to the core of the center of the moon, like 700 kilometers. And as you can see, in the Earth, we have a lots of earthquake happen on the surface. Not like moon, there are fewer shallow moonquakes happen on the moon. And also, you can see from here, the earthquakes happen on the Earth. Actually, it's always most of earthquakes happen on the moon. Actually, happen on the Earth. Actually, relative to subductive slab structure, and you can see the earthquake happen along the subduction. And the deepest earthquake by far in the record ever recorded only happened in the 700 kilometers depth. So far, we haven't detected any earthquakes in the deeper depth. And there are lots of reasons, but I'm going to not talk. But this is what we know now. But for the deep moonquakes, actually, they are really deep. They are deeper than a half of lunar radiance. And the funny thing, not funny, the interesting thing is that several of them actually have very similar waveforms. And I will show you later, no worry. And they usually like happen in a close area, so like the cartoon plus show here. So there are several deep moonquakes likely happen in a close area, and then we can look at this moonquakes, these several moonquakes as a one cluster, since they have similar waveforms and they have similar arrival times, and then we can treat it as a big as a one moonquake cluster. Here's some example waveform we recorded in the lunar seismograms. On the left here are the shallow moon. Actually, it's the impact data recorded in several stations. And here is another record plot done with Yuan and me. And then we are able to see that P and S arrivals in different stations. So actually, seismologists are able to pick P and S arrivals on the moonquakes. And here, this is a very good paper. If you are interested in the plantary, in the lunar seismology, I recommend you to read this paper. And actually, they have this nice summary process showing that here, this is the P and S arrival times for the shallow events. So this is distance, and this is travel time. And this is the summary plot for the deep events. So this is direct P, and this direct S. This is direct P, and this direct S. So as long as there's a P and S, seismology can use it to infer the seismic structures beneath the moon surface. Here it is. So this slide is showing several studies. So several studies have been used the direct P and S arrival that I just showed you from Apollo data, and to infer or forward the lunar seismic profiles down to about 1,200 kilometers depth. And there are some. This is some model, and this is P, and this is S. And we look for 1D. We won't look in 1D models. So we only care about the velocity variation as a function of depth. Although we are lucky to have a few stations on the moon, but to be honest, it's not as many as what we have to the Earth. So you can see the error bar of these seismic profiles are relatively huge. But luckily, the resulting seismic profile shows some similarities. And the right panel here is a summary of the source receiver seismic rate path for two particular models. And this is showing the upper one showing the red path of the P waves, the lower one showing the red path of the S wave for the Moonquakes and station layout, and the real data. So as you can see, the velocity models are different, slightly different. Your red paths actually travel different. So means that we might not be able to constrain lots of details on the moon, but we would like to use the scientists would like to treasure this data set to study the first big picture, the simple structure. When I say simple, means that only the velocity variation as a function vary as a function of depth. We don't talk about too much about lateral variation. This is what we did different for other planet, not like Earth. We have more data. Okay. And in this slides, I showing the example waveform from the shallow events and the deep moonquakes. And this is seismogram. So x-axis represents the time in minutes, and y-axis represented the digital unit. And you can please note that the y-axis, the range are different. So this is -50 to 50 and -10 to 10. So you can see that the deep moonquakes typically have lower amplitude and usually like a bit noisy because it propagates from the deep to the surface. And I think you already see that this is the wave field propagate for the one shallow event and deep moonquakes, because the source locates in different depths. So the waveform definitely will look different. Okay. Now I'm going to tell you the big differences between moonquakes and earthquakes. Number one. Here is showing the shallow events for the earthquakes and moonquakes. And they are all shallow. And the main arrivals marked in red. Please note, the time axis actually it is in different time span range. Now this is 30 minutes. In this plot, 30 minutes is here. On the moon, actually, there are special characteristics of the shallow moonquakes. You can see you have a very long duration. It can be 6 minutes, like in earthquake. No, we didn't see it. And the amplitude actually slow decay from the maximum amplitude to the end of the event. And also, you see the P and S, between P and S is not as clean as Earth. There are energy that gradually build up energy from the P and then going up on the here and decay slowly. And this actually we didn't see such of the waveform in Earth. So the characteristic of the moonquakes. And this can be explained by strong and lots of scatters energy. So this is a schematic representative of seismic energy propagate with the scatters. So if you have lots of scatters here, and the wave will bumping around, will bumping around, and the wave package will amplitude will decay slower, and that will stay longer. So that's one of the things that we think about the moonquakes. So that's the reason we think the moonquakes are different. The moonquakes have lots of scattering. So here is the simulation done by Maxon. And this is the no scattering, and this is scattering. As you can see, if you have scattering structure, and your waveforms will scale around, the waveform will look totally different. And it can be described by diffusion equation. Not only scattering, but also an elastic wave field. So this is another animation done by Maxon. Here shows elastic median Here shows an elastic medium. So seismic waves travel in the elastic medium, and elastic medium, actually the energy will lose due to the inelastic process. So if you can see here, actually the waveforms or the amplitude are still the same. For this one, the amplitude decays a lot. So this also can explain the amplitude decay phenomena. And this is summary prop by Longuin in 2012. And what they show here is that the moonquakes, earthquake, are also Mars, but we are not going to mention here. But when they plotted the scattering energy, the scattering and the absorption phenomena. And please note here, we all talk about the moon. Moon is totally different than other seismic events happen on the Earth and Mars. Is here. So you can see it has a lower diffusivity. When I have a lower diffusivity, means that very high diffusion. Very high diffusion means lots of scattering. So your energy will bumping around, and your waveform will look like a wave chain. Also, you can see it's a higher absorption. The higher absorption means very low attenuation. Now, a low attenuation means the energy won't decay as soon as what Earth does. So that's the reason moonquakes looks totally different than earthquakes. So since we notice that, so we know that there are lots of heterogeneities on the moon subsurface. And this surface layer, we call it lunar mirror. And in this layer, there's a lot of fine scale and frustrated, very fine scale stuff and fractured structure. So from seismology, from seismogram, we know that the moon subsurface is highly fractured. And the reason for that, maybe due to there's no surfacing, so now resurfacing, and also, as far we know, there's a lot of meteor impacts happen on the moon. And Galileo and Ludo in 2017, they also found actually this scatter energy actually not only shallow, it can be extended to almost 100 kilometer steps. Means that in this part, we can all call it lunar miracle. And in this area, we have a lot of scattering, and we have a lot of scattering. We have higher diffusion and lower diffusivity. And actually, this is like deeper than crust. So means that there's a lot of the uppermost moon subsurface. So like here, 0 to 100 meters depth. Actually, it might be showing lots of a fracture of the cracks due to in the crust or mantle due to the late heavy bombardment. So it's not only a fact for the shallow part, but also can go to the deep 100 kilometers depth. Professor Yi, I'm going to answer your question by this slide. Okay, most of the seismic events are deep moonquakes, and the amplitude are very small. And actually, I won't answer your second one. I go to the answer later. Okay, and these deep moonquakes are widely assumed is also associated with the lunar tides. The reason for that is, first, in the old days, so in the earlier study, they already noticed that the moonquakes happen. So this is the number of moonquakes in every non-nautical month. This is time and this number of moonquakes, and this is the Earth and Moon separation distance. And as you can see that the moonquakes actually happen periodically. And there are like a 27 days periodical, and this is the tidal effect by the Earth. And not only that 27 days, but also this 206 days. And this actually is the tidal effect by the sun. Not only the timing, but also Kawamura in 2006, they found out that the stress released from these deep moonquakes actually is very slow. And this is good, means that it's not like an earthquake. It's not like an earthquake. It's that the stress release is very fast and huge. It's slow. So, and actually it's similar to the tidal stress between Earth and Moon. And so what I say, these moonquakes actually very close to each other, so we can stack them. Here showing that I stack the, so here showing that three deep moonquakes there with a similar waveform with low data quality. But once we stack them, we can see the P and S arrivals clearly. So here shows the 38 moonquake cluster. So we call this a moonquake cluster because they stack lots of moonquakes. A moonquake cluster, we show 38 moonquake cluster location on the map view, and also the histogram of the depth of the moonquakes here. And as I showed you before, so we know the lunar interior in the Earth, in the earlier study, there are two things that are inconsistent a lot. First is the crustal thickness, and vary from 30 and 60. And I showed you before, the waveform looks, the ray path looks totally different. In addition to that, earlier seismic model usually don't have the resolution in the deepest moon. So there are several researchers, including me. We revisited the Apollo mission data, or some researchers even added more geophysical constraints, try to get better resolution for the crust thickness and also the core size of the core. Here I quickly shows the result for the crust thickness, and the upper one showing the seismic data, and result from seismic data, and lower one result from the gravity. And the comparison is here. And you can see that their results are very consistent, and it's about 30 kilometers thick. And this is the data, using the data generated by meteor impacts. And also, you can use other seismic methodology. And here is one of the methods, and Nogane using in 2003, they're using receiver function. And receiver function methodology is very sensitive to seismic discontinuities. So they try to model the receiver function with 30 and 60 thickness and compare with the real data receiver function. And they found that, okay, they look similarly, but if you compare the amplitude, the 30 kilometer step looks better. And also, while we have the GRACE mission on the Earth, in the 2011-12-ish, there's a Great Whale mission, and they do a very nice gravity surface of the moon, and then compare the gravity data and topography. They estimate the thickness of the 12 and beneath the crustal thickness beneath the upper 12 and 14 is about 30 kilometers thick. And the bulk crustal density is about 2,500 kilometers per cubic meters. So then these are all consistent. And this is crustal thickness. And go to the course. And due to our time, I will go quickly. So basically, we can use the seismic data or also gravity data as well. And we use the data I shared with you in the beginning, we use the reflection energy. So after 2011, two groups using reflection energy to looking for the core. So means that we stacked all the upper emission. If we get the right radiance, core radiance, we should see the coherent signals shows up. And this is the way we do it to find the direct the reflection energy from the core. And this shows the example. And then for this one, we see several peaks. So this is actually, I vary the moon radiance and from 0 to 700 kilometers. And this is the stacking energy. You can see several peaks here. And these 3 peaks actually related to different deeper layering structure. And this peak, because we have this peak, we didn't interpret it because we don't have a lot of traces. So after 2011, we revisited the data. 2 of group actually come out the core size, and with different model with different core size. And for this one, the results showing that lunar core, lunar core is about 330 kilometers radius. And for this one, and the roughly estimate is about 380, and also it may be smaller, 350. According to this one, these 2 results, it shows that one of the model thinks that the lunar core is maybe 30% of liquid. And for this model, they prefer that the core is mostly like liquid, and not only made by iron, but also made with a light element. And as what I said, we have more data from gray mission, and the result also showing that the core radius is roughly similar to what seismology observations. Okay, here is some conservative interpretation of our deep reflection in the lunar deep interior that we published in 2011. And we have these ideas based on iron and sulfur system. So we estimate the temperature in the inner core and outer core about 1700 kelvins. And the first partial melting zone is a bit lower, but and with different core radius. Okay. So I listed some take-home message here. First, seismic wave behave different in different planetary environment, and different seismic source exist in other planetary body. So if you go to another planet, you should expect other seismic signals. And also, the key things that lunar seismograms are characterized by strong scattering waves with long duration. And this mainly due to very, very low noise level and significant low and elasticity. Third, after revisiting the lunar seismic data, the seismology observations are able to detect subtle coherent signals which are related to a lunar interior structure. The core actually is really small. It's roughly about 350 kilometers. And the results are compatible with the other type of observation. And again, decoding the blitz pressure data carefully, since it's difficult to have the same station coverage on the Earth on other astronomical body as those on the Earth. And even though in the Earth we have instrument development, we have a more sufficient observation, and we have a good methodology development, we still don't know a lot about Earth. So we do the same to the moon. And that's all I have today. Thank you.
Thank you so much, Professor Lin, Patty. So we still have a couple minutes. Can you give a quick answer to why we only have a deep moonquake triggered by tidal stress?
Actually, not only deep moonquake. Actually, NASA's group they published a paper in 2000, I think 2018. I can find out later. They also trying to find the coincidence or coherence of the shallow moonquakes and and tidal force. Actually, they found out there are some events actually is related to the tidal force for the shallow events. So they interpreted that those shallow events actually generate by young faults, and these young faults actually have a cause by the tidal effect. So some of the shallow events, indeed, the researchers explained that they also happen due to the tidal effects, but not all, because all the things based on the periodical happen, the time happen. So they only can explain some of them.
Okay, Professor Wendy Jane has the last question. That is, she asked that now that the moon has a liquid core, why doesn't it has a magnetic field?
This is a good question. This is a good question. And Mars also has a liquid core, and it has a magnetism before. Okay, there are several interpretations, and I think I'm hiding a slide. I'm hiding a slide I can show here. So actually, observation point of view, lunar core didn't have a magnetic field, but the magnetic field was recorded as a magnetism by rocks on the lunar surface. So it can be the magnetization recording can be happen in two scenarios. One, moon actually has similar structure as Earth before, and the core is small. The inner core is smaller, and we can do the convection in the outer core, and it can generate its own dynamo. And there's another idea is that like Mars and also Moon, lots of researchers think about the magnetization. Actually, it only happens when the planet is partial melt. In the melt, when they smash around, the whole planetary body is in the magma. And when in the magma, when it's cooling, the magma actually, they are active and they can generate some magnetization, and it can be recorded in the crust. So there's a lot of ideas, and I just show it here. So we don't know which one is correct, but so far the record we don't have, and means that the outer core is not thick enough to generate the dynamo. Okay,
very good, Professor Lin. Because the time is very.
Sorry.
I mean, Dr. Simon Rock, he's waiting.
Oh, cool! He's still up. Happy.
He's here. He's here. Yeah, so that we can hear his talk. And so for those of us who want to ask Professor Lin further questions, we could write to her. Right? And I'm sure she would love to answer you and talk to you.